Hello everyone, welcome to the next lecture on the real analysis. Today I will explain you how you can check the uniform convergence by using the WM test. Myself Dr. Harish Garg, you can follow my YouTube channel where you can find the playlist of real analysis. In this playlist you can see the various lectures related to the pointwise convergence, uniform convergence, and we have discussed the state and proof of the WM test for the uniform convergence in our last lectures. Apart from them, you can also see the various lecture of the sequences of the functions available in this playlist. Now, we have defined that how you can check about the uniform convergence. We have discussed two different methods. First method is by using the definitions and second method is by using the WM test. In this lecture, I will cover the WM test, the various examples. However, for this method 1, I already explained you in my this lecture example of the uniform convergence. What is the WM test? If you have the infinite series summation of the Fn defined on the subset of the real line R such that the value of the Fnx is less than or equal to Mn, then we can say the series Fn is uniform convergent if my infinite series Fn is convergent. That's a simple result of this. And if you want to get the proof of this result, you can watch about my this lecture of the WM test. If you watch my this lecture, the proof is already given in this lecture. Now, I will explain you with the help of the numerical examples. Firstly, I will tell you the two-step rule. Step number 1 is you have to find the value of the Mn. Step number 2, we will check about the convergence of Mn. Now the question arises is how we can check the convergence, how we can find the value of the Mn from the given series Fn. So we can apply the definition. If we start with the modulus value and we prove that it is less than or equal to Mn and this number is in terms of n, then in terms of the n, then we can say the Mn we have defined. Second step is we will check the convergence. Again, how we can check the convergence? We can use either the root test, ratio test, geometric test, limit comparison, and many more available. For more detail about this testing, you can watch again the same playlist, and you can see in this playlist I had uploaded the complete testing or complete convergence analysis on this Leibniz test, Cauchy integral test, ratio test, root, limit comparison, geometric, all I have explained in this playlist. So let's start with the first question. Discuss the uniform convergence of the series. First of all, what is the domain? Domain is not given, so it's a complete real line R. What is my Fnx? This, if I compare the series with the Fn, this number is my Fn. Now I start with the value of the Fnx. The modulus value is 1 over 2 raised to power n cos of 3n of x. My target is to prove this is less than equal to something. Fine. Since we all know the value of the cos is always be less than equal to 1. Fine. So I can write this number is 1 over 2 raised to power n. And this is the only term which is dependent on the n. So I call this is my m. Step number 2, we can start with the series. What is the value of the Mn? Is 1 over 2n. Clearly say this series is my convergent. Can you tell me why it's a convergent? Because by the geometric test. What is the geometric test? What is the common ratio of the geometric test? In this case, the geometric ratio is my half, and you can see the value of the mod of R is my less than 1. Therefore, by using the geometric series test, the series is convergent. Therefore, by using the WM test, the given series is also uniform convergent. I hope you don't forget to like and comment on this video. Again, you can see that my series is defined on the R. This is the value of the Fn. I can start with the Fnx. I can substitute the value of the Fn. Now, your target is to write this value in the terms of less than sign. But since you can see x belongs to the real number R, so that means x square is always my positive number. Fine. N is also my positive number. So all these quantities my positive. So I can write the firstly this expression is outside the modulus. Now because x square is always be greater than 0, what does it means? Because my target is to write in the terms of n only. That means I have to eliminate x. X square plus n is always greater than of the n. Fine, for all x. Look at the second case. X square is greater than, so if I add of the nx, this is always be greater than of the n provided x must be greater than equal to 1. Fine. So what do you conclude from this case? So from this I can write 1 over x square plus n is less than equal to 1 over n. From this case I can say x square plus nx is less than or equal to 1 over n for all x greater than equal to 1. I can substitute this value. It is 1 over n into 1 over n, that is 1 over n square, and that I call as the m. Fine. Now once you know the value of the mn, I can start with this series. This is representing as n square, and clearly say this series is my convergent by which test? You can see by using the p test. If you remember that, I can recall it quickly. What is the p test? If 1 over n raised to power p is convergent provided p is my greater than 1, this series is my divergent provided p is my less than equal to 1, and in this case you can see p is my 2 which is greater than 1, therefore this series is my convergent by p test. Therefore by using the WM test, the given series is convergent for all x greater than equal to 1. Again, to test the convergence of the series, this expression is represented by Fn. I can start the value of the mode of Fn. Again, x belongs to the real line R. Then we can say x square is my always the positive number. So this value is my positive because n is my natural number which is always greater than 0. This number is my positive. This number is my positive. I can say this number is outside the expression. Since x square is my greater than equal to 0, this implies x square plus n is always greater than of the n for all x. Also, x square plus n plus 1 is always be greater than of n plus 1, and n plus 1 is always greater than equal to n. So I can substitute this value. It is 1 over less than of 1 less than of the 1, that is 1 over n square, and I call this number is mn. Now once you know the mn, we can see this series is my convergent by the p test again. Therefore by using the WM test, the given series is uniform convergent. It's for all x belongs to the real. Look at this one. Test the uniform convergence of the series. Clearly say this function is my fn. So now I can start the value of the fnx. I can substitute this sign of nx divided by n raised to power p. Fine. Now we all know that the sign value is always be less than 1. Remember always your target is to write the value in the terms of less than sign. Fine. And the given series mn, which is 1 over np, and it is given that p is my greater than 1. So that means this is by convergent by using the p test. Therefore, by using the WM test, we can see the series is uniformly convergent. Test the uniform convergence of the series. So in this case, your target is to write the value of fn firstly. Now you can see that. How you can write the value of fn? It's a 2, it's a 4. So 2 raised to power 1, 2 raised to power 2, 2 raised to power 3. So 2 raised to power n. Look at the value of the x. X raised to power 1, x raised to power 3, x raised to power 5. So that's the odd series. I can say it's a 2 raised to power 2n minus 1. Denominator 1, x square, x4, x6. That's the even series. So it's a 2 raised to power n. Fine. Now we can start with the modulus value fnx, which is equal to 2 raised to power n, x raised to power 2n minus 1 divided by 1 plus x of this. Now clearly say, because x is lies between minus 1 by 2 to plus 1 by 2, so that means 1 plus x raised to power 2n is always my greater than 1. Why? Because x square is always my positive number. What does it mean? 1 over 1 plus x raised to power 2n is always less than of the 1. So I can say this number is always less than equal to 2 raised to power n into x raised to power 2n minus 1. Fine. Again, because x is my less than of the half, I can substitute this number also, 2 raised to power 2n minus 1. So I can simplify this. This value will be by 2 divided by 2 raised to power n, or I can say it is 1 over 2 raised to power n minus 1. Now this is the function of the n. I call this is my m. Fine. Now can you about this series? This series is my 1 over 2 raised to power n minus 1. Clearly say this is my geometric series. Fine. And what is the common ratio? Common ratio is half, and the absolute value of the r is my less than 1. Therefore, the given series is my convergent. Once the given series is convergent, therefore the series Mn is convergent. Therefore, by using the WM test, we can say the given series Fn is my uniform convergent. This is the first method. Fine. This is the first method, you can approach this manner. Second way is, you can also consider this value is my Mn. That's on your choice. You can consider this value is my Mn. That means your target is to check about this series. Fine. Now how you can check about this series, whether it's a convergent or not? We can apply the ratio test. What is the ratio test? If I start with the Mn plus 1 over Mn, if you prove that this number is less than 1, then it is convergent. So I can substitute the value of Mn plus 1 into x 2n plus 1, 2 raised to power n, x raised to power 2n minus 1. So which is my twice of the x square. Now clearly say x is lies between minus half to plus half. So x square will be lies is 1 by 4. So if I substitute this number, it's a 2 into 1 by 4, that is half, which is less than of 1. Therefore, by using the ratio test, the given series Mn is convergent. Hence, by WM test, this series is uniform convergent. This is the second method. You can apply the ratio test. Fine. The first method is you can substitute the value of the x directly less than of the half, and then you can apply the geometric series test. Okay, again the next example is test the uniform convergence of this series. This is my Fn. So I can start with the value of the Fnx. Fine. My target is to prove less than of the sign, and we all know the value of the cos is less than equal to 1. So this is 1 over n into n plus 2. Again, we all know n plus 2 is always greater than n. So n plus 2 is less than of the 1 over n. So this number is again 1 over n square, and this number I can take as a mn. Otherwise, you can also consider this number is my mn. That's on your choice. Fine. So now clearly say the series Mn, which is 1 over n square, is convergent by using the P test. On the other hand, if you consider this is my Mn, then can you prove the convergence of this? So clearly say you can take the limit comparison test. Fine. Like un will be your 1 over n into n plus 2. Vn will be your n 1 over n square. Then un over vn, it goes to the 1, which is finite, and you can see this is by convergent by the limit by the P test. Therefore, the series un is also convergent by the limit comparison test. Now once the Mn is convergent, therefore by using the WM test, the given series is also convergent. Okay, look at this another one. Test the uniform convergence of the series provided A is lies between 0 and 1. this number is my fn. So let's start with the value of the mode of fnx. This number is sine of x over n square. Fine. Now if you think about that, this number is less than equal to 1. Now it is independent of the n. My target is to write this quantity in terms of the n. So that means, because we all knows the value of the sine x is always be less than equal to x. Fine. So I can say this number is less than or equal to x over n square. Fine. And what is the value of the x? Minus a is less than x is less than a. So I can say this number is a over n square. Now clearly say this number is my function dependent on the n. So therefore a over n square is my m. You can check about the series convergence. A is my outside and clearly say this is my convergent by using the P test. So once the Mn is my convergent, hence by the Wm test the series is uniform convergent. It is not for all x in the R, it is for all x belongs to the minus a comma a, where a lies between 0 and 1. Show that the series is uniform convergent or for all theta belongs to the R. This is my Fn. Now let's start with the value of the Fn of, instead of the x, it is my Fn of theta. So I can start with this value. Clearly say cos theta is my less than 1. It is my R raised to power n. Then I can start with the Mn. Now clearly say again, this is my geometric series. Fine. And then the common ratio will be my R, and R is lies between 0 and 1. Therefore, this series is my convergent by using the geometric test. Once this is a convergent, therefore, by the Wm test, the series Fn is also uniform convergent. If the series summation n is absolute convergent, then prove that these are my uniform convergent. Very, very simple. What is given to you? What does the meaning of this series absolute convergent? That means the series is my convergent. That is the definition of the absolute convergent. Fine. Now let's start with the given first series. Then for the first series, this is my Fn. So let's start with the Fn x, which is my an cos nx. I can say this number is my an into cos nx, and the value of the cos nx is always less than of an, and clearly I call this number is my mn because this is a function of the n only. Now your target is to check about the convergence. So what is the m? And it is given that this series is convergent. So once the m is convergent, therefore by Wm test is a uniform convergent. Similarly, that you can prove it by on. I consider this is my Fn. Again, instead of this cos is a sine. Again, you will get the same expression, and hence is a uniform convergent. Look at this another one. Show that the series converges uniformly over the domain x close interval 0, 1. This is the value of the Fn. So I can start with the value of the Fn x, which is x raised to power n 1 plus x raised to power n. Fine. My target is to write this in terms of less than sign. So clearly say x is lies between 0 and a. What does it mean? 0 x raised to power n. Fine. What does it mean? If you add the 1 on the both side, it will be 1 plus a raised to power n. Now if you take the reciprocal, it is 1 plus a raised to power n is less than of 1 is less than of 1. If the equality appears, you can write it also as the equality because it's a closed interval. Fine. Now clearly say I can return 1 over x, this value. This number is less than of, and moreover x is positive number. So I can also say this number is x raised to power n, and x is less than of the a. So I can say this number is also less than of a raised to power n. Fine. Now this is my Mn, and you can see what is the series Mn, series An, and this is my GP series. Fine. And what is the common ratio? Common ratio is A. So what is the value of the mod of A? And A is strictly less than 1. Therefore, this series is my convergent by using the geometric series test. And once the Mn is convergent, therefore, by using the Wm test, the series is uniform convergent. Make sure, student, in order to check the convergence, I recommended you can watch about my this playlist about the complete nth geometric limit comparison root ratio test complete about this playlist. I hope you can like and comment on this video as well. We will see the next lecture on the various properties of the series of the uniform convergence. Till then, you can share this video with your friends and don't forget to like, comment and subscribe my YouTube channel. Thanks for the watching and thanks for the support always. Happy learning, students. Best wishes.